All right, welcome back to the probability slides. Let us finish them up. So one of the last things we talked about was conditional probability, probability of E given F. If we know that F occurred, what does that tell us about whether E occurred? So that's helpful. That's the formula for conditional probability. I want to show you a way to flip it around. So if you know like probability of B given A and some other things, then you can flip it around and solve for the probability of A given B. Maybe that's what you really wanted. Okay, we can do that with this formula. Here it is. It's called a Bayes theorem that tells us why this is possible. But the probability of A given B is equal to this, probability of B given A times probability of A over the probability of B. Okay, and let me prove that to you. The way you get it is you use the definition. So then you unpack it. You solve for some stuff. So here's the formula, right? Probability of E given F is all this. Let's just translate that into the probability of B given A. That's the one we claim to have. So if you have that, that means you know, right? Another way to formulate that is B given A. That's equal to the probability of B intersect A, but that's the same as A intersect B, right? It's commutative all over the probability of A, because that's the thing to the right. Okay? And then I can take this, I can multiply by the probability of A on both sides, and I can get the probability of their intersection by itself, right? That would be P of A times probability of B given A is equal to the probability of their intersection, all right? And then I can make that same formula for the other way. Like probability of A given B has a lot in common, right? A given B, that's equal to the probability of their intersection over the probability of B. And oh man, I can take this equation, this part right here for the intersection, replace it with this, and that's why. That's why you can do that. Okay, so that's the formula. That's called Bayes' theorem. It tells us that we can switch things around if we know a few things. A fun way, technically, I mean, you need these three things or something that's similar. Okay, so maybe if you don't know the probability of B, you'd want to divide by it normally, right? If you don't know the probability of B, you can get away by knowing the probability of B given A complement, A not occurring. So that's one way to switch things around. It changes a little bit. You can solve for the probability of B if you knew that. Right? It's going to be the same as the probability of B given A times the probability of A plus the probability of B given A bar times the probability of A bar, which you can compute this one, right? This you can get easily from the probability of A. Just subtract 1 from it. If you have this one but not the probability of B, you can solve for the probability of B using the other things you know you have. So that's pretty nice. So let me prove that to you. Like, why is this equivalent to the probability of B? So here's A, here's B. Here's my silly example. So the probability, we're trying to solve for the probability of all of B, right? We don't know it. If I know this, right, the probability of B given A times the probability of A, that is going to be, that gives me the probability of their intersection, right? That's that. So I get the probability of their intersection with that bit. That's the left bit. So I have that. And then, this other one, I'm going to get it in a different way. The probability, that's going to give me, you see how this is going to give me the probability of, A bar intersect B. For the same reason, like the same reason that this is going to give me the probability of A intersect B. And this is kind of the formula. Probability of B is equal to these two things. It's everything that B shares with A and everything that B does not share with A. Because like what's A bar? It's everything that's not in A, right? This is A bar, including all this stuff. And then A bar intersect B, which we're getting with this, is just like this bit. This is still A bar. A bar intersect B is all these guys, right? All the diagonal lines meeting the other diagonal lines. So that's going to give me that. And do you see how together now, like where they overlap, if I add them up, I get the probability of B. So that's another way to solve for something if you didn't have it. If you didn't have it, you can still use the formula and like replace that with what you had. Okay? So that's Bayes' theorem. It's very useful to be able to switch it like that. So a very classic example of solving something using Bayes' theorem, using this ability to switch the conditional probabilities, is to determine how good a test is for some illness. Let's say like the next COVID happens, unfortunately, and let's say that we made a test for that new virus or whatever, and let's say that test that we make is 90% accurate when somebody has the illness. It's good at telling you when somebody has the illness. It's 90% accurate. It's 90% going to tell you that they're positive, right? So the probability, what that's saying, right, is the probability of the test being positive given that you had the illness. That's 90%. That's exactly what that's saying. I hope that makes sense, right? And then also, hopefully, this will be true about the next pandemic, but it's only present in not too much of the population, this illness, all right? So let's say that it's only present in 5% of the population. So the probability that you have the illness just in a random sample of people is 5%. So just has illness in general, that probability is 5%. And so that means the probability of you not having an illness, just in a random sample of people, is 95%. So that's good, okay? So those are those probabilities. And now, let's consider that suppose that the test is 80% accurate when somebody doesn't have the illness. So it's not quite as accurate when you don't have it, but it's pretty accurate still, right? So that means the probability that the test is negative given that you don't have the illness, that's 80%, all right? Which also means you can flip it around, right, by subtracting the complement. That would say that the complement of that, the 20%, that's it being positive, right, given that you didn't have the illness. So the probability that you get a positive result back, like a false positive, given that you didn't have the illness, is 1 minus this. Okay, so that's 0.2, 20%. And so now what we really care about, like we have this, we really want it the other way. What is the probability that somebody has that illness when the test gives back positive? Because that's what it means to be a good test, right? This is harder to calculate. This is harder to like get from a sample. So we can get it by using all these other pieces, okay? And that's equal to, right? It's going to be the probability, right? It's going to be this Bayes theorem. Probability of the other way times the probability of that thing, right? So it's going to be, that's equal to the probability of the other direction. Probability that's positive given that you have the illness, which we know, times the probability that you have the illness. We also have that, okay? I'll just call it high for has illness. We don't actually have the probability that it's positive. We don't have that here, but we have this second thing, okay? And so that's what we're going to use to get the probability that it's positive by using these other two pieces, all right? So that's going to be, all right, the probability that it's positive is the same as the probability that it's positive given that you have the illness times the probability that you have the illness. So that's what A and B are right now. The probability that it's positive given you have the illness, you have that, times the probability that you have the illness. So that's all the things that we already put up top, plus the probability that it's positive and you don't have the illness, no illness, right? Probability that it's positive and you don't have the illness, no illness, let's say, Ni, times the probability that you don't have the illness. So you see how that's going to be the complement there? And so that will give us the other side, and that will give us the probability that it's positive in general. So that's perfect. So that's what we want. That's what we want to calculate. And so let's solve for these question marks by filling in all this. All right. So that's going to be, this is 90. This is 0.5 or 0.05. All right, over that all over again. 0.05. And then plus, this is positive given no illness is 0.2. Times 0.95, right? That's the probability that you don't have the illness, no illness. So let's solve for this. So what's the probability that you actually have the illness given that you got a positive test result back? Tells us how good the test is. All right, there's some other files that I'm going to show you later there. But let's do this one. It's going to be, let's see, we've got 0.9 times 0.05 divided by also 0.9 times 0.05 plus, this time though, 0.2 times 0.95. And that is 19-ish%. Disgusting. 19%. So this is actually a pretty bad test, even though these numbers look pretty good. So the probability that you actually had an illness, had that illness that the test was supposed to tell you if you had it, given that you got a positive result back, was really only about 20%. Not a very good test. And the reason why is the fact that it's very common to not have the illness. That's what leads, that's what means, that's what's going to tell you that the false positive rate is kind of a little too high, okay? Just because it's very unlikely to have the illness and that it is possible to get a false positive, right? It's like a 10% chance or something. Right, this way, false positive. It's a 20% chance you get a false positive, even if you're one of the 95% of people that didn't have the illness. So even though the numbers look good on paper, like what you really wanted to know, like if you had the illness, given that you got a positive test, it wasn't a very good test at the end of the day. So that's kind of fun to think about. It's a common reason to like look to Bayes' theorem. It's a great way to motivate the topic. So good for stuff like this, good for trials where it's like, it's easy to calculate this, but it's very hard to calculate the other way. You can solve for it. That's pretty cool. All right. Well, let's next talk about what's called a random variable. All right. It's just, it's always a capital letter. So a random variable is always a capital letter. But the letter is really short for a function. It's like x is a function from the sample space of your experiment, like the possible outcomes that you could have, to the real number. So it's giving a number, kind of probability almost in a sense, but at the same time it's not. It's just a number that represents something that you're trying to count, usually. So it's a function from the sample space to some number that you get to define what the number is, all right? And I want you to think of it like it's a variable whose value you can look at, and it's always different. Like it's random. It's like a random number. You look at the value of the variable, you print it out, it's like different every time. It's supposed to be a random number, okay? And so that's interesting to think about. And you can ask for the range of the whole thing by like plugging in the sample space. You can give it a whole set of things. That tells you like what could it possibly give back. Okay, so here's a example random variable. Let's define the random variable d to be a function from the sample space. So you give me some event that took place, and what I'll do is I'll add up all the numbers on the dice. Like that's what my number, that's what I want my random variable to represent. All the numbers added up on the die for this particular event. So if this is event E, what should the random variable give back? What should we define it to give back if this was the outcome? Well, the sum of all the numbers on those dice are 9. Okay? So that's one value that the random variable could take on. It's just like it's meant to keep track of all the possible different ways that you could get numbers back by rolling 2 dice and adding them up. Okay? And then here is another outcome, like D could take on the value 5 just as easily because you could have landed on a 3 and a 2. So that's a random variable. Okay? And so that's that one. Yeah, so that was the book example. It's like you make a random variable D to represent rolling 2 dice. And so the number that the random variable gives back when you look at it, like you have to inspect it and it changes every time. It's like Schrodinger's cat experiment, if you heard of that. It's like different every time. You got to look at it to see it change. And so like the number that the random variable gives back is the sum of the numbers on the dice. That's what we're going to randomly, or that's what we're going to define it to be. That's what the random variable means. So like it could give back 5, it could give back 9. But like the lowest number it could give back is 2. The largest number it could give back is 12, because like 2 6s, right? So like that's the range of the random variable, and you can get that by plugging in the entire set. Okay, that's another way to do it. Another example from your book is like you got 2 spinners. You got a blue spinner and a red spinner, and they can land on the numbers 1, 2, or 3, each of them. And so we could make a random variable, call it m, to be the random variable that represents the sum of the value that the red and blue spinner landed on. So for example, m on like 3, 2, that would give back 5. Okay, that's the idea. And yeah, you just give it the whole sample space if you want to see the range. Like if you give the entire sample space of like the different dies that you could give here, it's like that's the syntax. That will produce for you the possible range of the random variable. It tells you all the values it could take on. Okay, so yeah, let's talk about the distribution now of a random variable. So if you have a random variable, you can ask about like how often is it for the random variable to end up with a 4, end up with a 5 as the answer, 6 as the answer, for example. So the distribution is kind of like a bar chart in a sense, but we can write it out too. It's just the set of all the different pairs of like the value that the random variable could take on R, and then like the probability that the random variable really ended up being that answer, right? For every possible outcome, output of your random variable. So here's like, this gives you the range, right? And this gives you the range of that random variable x. So give me a value. Tell me how probable it was to land on that value. It's just the probability of each value that it gives back. Okay? That's what's going on there. Probability of each value, right? Each random output. So, okay. For these spinners, for example, this is, let's say this is random variable m that represents the sum of all the values on the spinners. So the output, the range, right, is 2 through 6, because you could roll 2 1s all the way to rolling 2 3s. So the numbers in between are counted too. So you can get a 2 through a 6. And so the ways, what are all the different ways you could get these? Let's determine the probability here. So what are all the ways that your random variable could be 2? Like, what are all the ways that m could give back 2? Well, it's only if the blue spinner was a 1 and the red spinner was also a 1. You see that? There's only one way to do it. What are all the ways for the random variable to be 3? Well, it could either be, the blue could be a 1 and the red could be a 2. Well, it's got to be a 2 and a 1, right? Or a 1 and a 2. Or the blue could be the 2 and the red could be the 1. That's the only way for them to add up to 3 and have the random variable give you back that sum, right? And then finally for 4, like for similar reasons, like what are all the different ways to land on 4? You could either do a 1 3, a 3 1, or a 2. They could both be 2s. And then for 5, like these are your ways to get 5, and then there's only one way to get 6. And then once you've like enumerated all the possibilities, then you know, like, all right, there's 1 2 3 4 5 6 7 8 9 options total, and there's only one way here, so it's a 1/9 chance that the random variable landed on a 2, gave back a 2 when we looked at it, when we looked at what the spinners gave back. Likewise, there's a 2/9 chance, right? There's 2 ways to get the random variable to give back a 3, because that's going to be the sum of those spinner values, okay? And the 4 is the most probable one, because it's got 3 out of 9 chances, so a third chance that the random number gives you back 4 when you inspect it and you look at it. You print out the value, okay? So those are your distributions, and then we can talk about the expectation of a random variable. The expected value, we say, of a random variable, this is the syntax, it's always e, and then the random variable goes between brackets. Like e, expected value of x, the random variable. You can define it in one of 2 ways, and one way is much easier. All right, so here's like the harder way, but like the expectation of a random variable is like, what's the value, on average, what value am I going to see when I look at the random variable? That's all it's trying to tell you, okay? It is just a weighted average at the end of the day. So it's like, give me every option in the sample space, every outcome of my experiment, and like multiply by the probability. Give me the answer, like what the random variable gives me back for that value, and then multiply by the probability that it gave me that value. Okay? That's what it's doing. Our P of S is the probability of the outcome S. It's just a weighted average. That's one way to do it. Or it's slightly easier to do it this way when you have the distribution ready already. It's like here, for every value that the random variable could take on, sum up that value times the probability that it landed on that value. So that's another way to write it that's equivalent, and that's easier to solve for. But at the end of the day, it really is just a weighted average, okay? So like here's the expected value. Like what, on average, when I look at the value m, that's supposed to represent these 2 spinners and what number it lands on their sum, what do I expect to see on average? What's the expected value of the random variable m, right? And so let's do it this way. It's the weighted average over all these possibilities. It's well, it could be 2. The random variable could give back 2 with a 1/9 chance. That's what it's saying there. All right, 2 with a 1/9 chance. There's one way to do it. All right, you give back 3 with a 2/9 chance. You add that up. Give back 4 with a 1/3 chance. 5 with a 2/9 chance. 6 with a 1/9 chance. If you add all this up, it gives you that weighted average, and it looks like 4, which makes sense, right? It's the most probable one. It's kind of like it's an inverse, it's like a bell curve there. And so it's going to land on the 4, most likely. Like that's the value you expect to see on average from your random variable m. That's what it's saying. Okay. You can also ask for the conditional expectation. It's like, all right, what's the expected value of the random variable m when I know that the blue spinner landed on a 1? Because that'll change things, right? So if the blue spinner landed on a 1, I know I'm either in this outcome, or this outcome. Those are the only options where the blue spinner landed on a 1. And so you can now ask for new possibilities, right? There's 3 options total when this is happening. And so like it could land on a 2 now with, well, now it's just a 1/3 chance if you have only those 3 options to choose from. could land on a 2 with a 1/3 chance. It could land on a 3 with a 1/3 chance, right? Because there's only one outcome where it lands on a 3 in this case that we're conditioning on. And then finally plus a 4 times 1/3 there. It could land on a 4 with a 1/3 chance because there's only 3 options, and that was one of them. And so I think it's not hard to see that this is going to give you back a 3. Like, you expect to see a 3 on average when you're looking for the value of m, the expected value of the random variable m, when you know that the blue spinner is landed on a 1. You expect to see a 3 on average. That's just your weighted average. Okay? So yeah, that's random variables, their expectation. It's really just a function, right? That you have give back a number that represents something about what happened in your experiment, like the sum of the dice or the sum of the spinner's values. You could do the product. It doesn't matter, okay? So here's one where we do the product. Here's a question for you. So consider an experiment where we've got a red die and a blue die, and you're throwing both of them. Let's call x the random variable where the value that x takes on is the product of the numbers on the red and the blue dice, okay? So like, for example, the random variable x, like one of the outcomes is like the red die lands on 2 and the 3 die lands on 3. So the value that this random variable will take on with that outcome is the product of those numbers, which will be 6. Okay? So figure out what is the range of x. I think it'll be helpful to write a program, so try that. And then give the distribution over that random variable x, like how often is it going to take on those different pieces, like draw this kind of table in some way. And then calculate the expected value of that random variable x. What is its weighted average? On average, what output of x should I expect to see? What's the, on average, like what number should it give back? What's the average product of those numbers for rolling 2 dice? Okay? So give that a try. And I think writing a program will help. And here's my program that I wrote here. It's going to solve for everything. So here I am. I'm rolling 2 dice. Like here are my total outcomes count, and I'm keeping track of how often each outcome occurred. It's a hash table in Racket. So I've got an I die and a J die, and they're ranging between 1 and 6. And like the event that just took place is like I just rolled a 1, 2, I rolled a 2, 3, whatever that is. So I'm keeping track of it like that. And then the product that it landed on was just like that's the output of the random variable. That's like your I times j, the numbers that the dice landed on multiplied together. And then I'm also going to keep track of the total outcomes, which I could have just hard-coded because I know it's going to be 36 options total, right? But yeah, I'm just keeping track of how many times I saw this product, right? How many times I saw it. I'm adding maybe an existing count if I found one, 0 otherwise. I'm adding it to that, okay? My new count is that plus 1. And then I'm keeping track of my expected value. It's always going to be updated. At the end, it'll have the right answer. Okay? So like I'm going to add in a weighted sum to this variable. And so like for every outcome, I'm going to take that expected value and multiply it by the outcome. Or I'm going to take that expected value, I'm going to take each outcome, multiply it by the probability that it occurred, right? How many times I saw it over the total outcomes, and then add that into my expected value sum. Okay, that's what I'm keeping track of. So you can write a program that does this, not too hard. That's what happens there, and then here's the output. So it's trying all my possibilities, and it looks like there's only, it's a hash table, so it's doing things in a weird way. So like the largest value you can get back is 36, and the lowest value you can get back is 1, because 1 times 1, right, is 1. 6 times 6 is 36, and here are all your different outcomes. There's not exactly 36 of them, but like as far as the number on the random variable is concerned, but there's 36 trials total, right? There's 36 ways of rolling 2 dice. So that's your total still. And then it's like, all right, the random variable could be 1 with a probability of 1 out of 36. The random variable could be 2 with a probability of 2 out of 36, because like you could have rolled a 2 and a 1 or a 1 and a 2, right? And then it looks like there's a couple different ways to roll a 6. There's 4 different ways to roll a 6. You got your 2, 3, 3, 2, or your 6, 1, and your 1, 6, right? There's 4 options there. And it's like, here are all your options. I'll just give you a screenshot here. Like, this is what you can solve for. And then to build up your answer there, you just like put it in a table. Oh no, is my beautiful drawings too far over here? I'll make this a little bit smaller actually anyway. There's the output there. And so just by doing that weighted average, weighted sum, you could like this is the range right here, right? It's going to be your range. These are the different possibilities you can see. And then this right here is the distribution. Like how many times is it possible to get a 1 as your output, a 36 as your output? It's just got to be one option, right? 10 has got to be like 5 and 2 or 2 and 5. You only have 2 outputs there. And so like there's your distribution. And then the expected value is that weighted sum. All right, and so you can solve for that. And that's apparently 12.25. Like when you look at x, that's the expected value that you see on it. 12.25 on average. That's the value you're getting back when you look at your random variable. That's like the middle of the road for the product of the numbers on 2 dice. Okay, so that's going to be your output there, and that's what random variables are all about. So yeah, I think that's what I wanted to say there. I hope that makes a little bit of sense. Next, let's talk about a topic called the linearity of expectations. All right, so let's say we got 2 random variables, and they're using the same sample space. So it's like x gives back a number given an outcome in sample space S, and y gives back maybe a different number. All right, you can ask for, since they align like that, you can ask for what's the expected value if you were to sum up those random variables values. And actually that's it's nice that you can, there's a proof to this, but you can actually distribute that expectation. The expected value of the sum of the random variables is the same as the sum of their expectations. That's pretty nice. And then there's also, if you have a constant, what's the expected value of a constant times a random variable? You can actually take out that constant. You can bring it outside. So that's the same as that constant times the original expected value of the normal variable by itself. Okay? So here's a proof of each of those. It's not too hard to see, just unraveling the definition of expected value for each variable. So let's do it we'll do it this way because it breaks down easier. We'll use this kind of equation. So the expected value of x plus y, well, just unraveling the definition, it's like for every outcome in the sample space, it's, well, this, right? What does x give back for it, plus what does y give back for it? That's the value that it takes on for that outcome, times the probability of that outcome, right? And this is just a number. These are just numbers at that point, and you can use the distributive property of addition and multiplication, right? Or of multiplication over addition, I think is the right word here. And then like you end up with this summation, right? But this summation is really just made up of 2 separate sums. You can split them up into 2 separate summations, one for each part of that sum. That's not too hard, right? So now you got 2 separate things. But these definitions, right, are exactly what it means to be the expectation of x. That's that one, right? And then the expectation of y is this guy. See it? That's really not too bad. So that's pretty cool. So that's why this one works. You can just bring it out. You can distribute the expectation, I guess. And then for the constant, it's very similar. It's just like, all right, what's the expectation? That's the expected value of the random variable times some constant always. It's like, all right, well, here's the value for each outcome in the sample space. It's, well, take what it normally gives back, multiply it by c, and then multiply that by the probability of that outcome. Well, these are now just numbers. You can bring that c outside, right? Just like anything else. It's a constant. It's always there. You can bring it outside of the summation. And then you have just this bit. And this, of course, this whole thing right here, that turns into just the expected value on that normal variable. And so that's why those both hold. And that's useful for us because it lets us solve some problems very quickly. And we can get some pretty impressive results without doing a whole lot using the linearity of expectations, as well as just expectations in general. So here's a fun little problem that will be very similar to the birthday paradox. So here, for this example, let's pretend that the probability that somebody's born on a given day is 1 over 365. Let's just, sorry if you were born on the 29th of February, let's just do this because it's easier. The math is much easier. So the question is, in a group of 100 people, what's the expected number of pairs of people who have the same birthday? So you see how it's similar yet different to the birthday paradox? So it's like, what is the, on average, how many pairs of people can we expect to have the same birthday? Okay, so this is like a counting problem plus expectations problem. So first of all, how many pairs of people are there in a group of 100? Because that's what we care about, that, and there's 100 of them. So how many pairs of people are there in a group of 100 people? There are 100, choose 2 pairs of people in this group. Okay, and so if you do the math, that's equal to 100 times 99 over 2 factorial, so just like over 2, right? Over 2, that's a 0, over 2, which is equal to 4,950 pairs of people in a group of 100, all right? And the trick is, to solve this very simply, is to make 4,950 random variables. Okay, so watch. Here's how you can solve it. What we do is let's make a bunch of random variables. P1, P2, they're all going to correspond to one of these pairs. P1 for the first pair of people, P2 for the second pair, P3 all the way to P4950. So our random variable for each of them, let them be random variables that, well, what numbers do I want these random variables to take on? I want them to be 0, because I want to be able to add them up, right? Add up their expectations. I want to be able to make these be 0 when that pair does not share a birthday, and 1 if they do. So random variables that are 0, because that's all a random variable is. It's a value that you can inspect that gives you back a number. And let's make it be 0 if that particular pair, if the pair doesn't share a birthday. And 1 if they do. Do you see how if I were to add these up now, it would give me like, and I do it a bunch of times across a bunch of trials, I get like on average, how many, right? How many people have a birthday in common? Because it would be 1 if they do share one, 0 if they don't. And so what I really want is the expected value. I want the expected value of these random variables summed together, because that would give me the expected value for how many pairs of people share a birthday, right? Expected number of all of them all at once. So what I'm after is this. I would like to know the expected value of adding up these random variables, P1 plus P2, for all these pairs of people. Because sometimes it'll be 1 if they share, and it'll be 0 if they don't. So on average, like, what is this sum? Because that'll tell me how many pairs, right, shared a birthday. And so I can use now linearity of expectations on this guy. Because like, all right, if you want the expected value of a sum of random variables, you can bring the sums out. You can just bring the expectation to each of them. So that's equal to the expected value of P1 plus the expected value of P2, right, all the way to the expected value of pair 4950's random variable, 1 if they share a birthday, 0 if they don't. And now I claim that all of these expected values are exactly the same number, right? What's the expected value for pair I to share a birthday? Well, it's equal to, right? How do we calculate the expected value? It's equal to the probability, like for every outcome, it's equal to the value of the random variable at that outcome times the probability that the random variable took on that value, right? So we either are going to get a 0 back or a 1 back from this random variable. That's how it's defined, right? 0 if they share, 1 if they don't. Or sorry, 0 if they don't share a birthday, and 1 if they do share a birthday there. And then we're going to multiply that by the probability. Like, what's the probability that this pair of people don't share a birthday? Well, it's pretty likely, right? 364 out of 365 chance that they don't share a birthday. But there is a 1 in 365 chance that they do, right? It's like they're both born on the same day, right? That's how you pick that. That's the odds that a pair of people were born on the same day. If they share that birthday, it's 1 over 365 chance. And the expected value is this weighted average, and the 0, of course, that all cancels. And so the answer for the expected value for each random variable is 1 over 365. And so this means this is just 4,950 times this is your expected value. Right, and that's equal to 4,950 times 1 over 365, which is equal to, on average, we have 4950 times 1 over 365, 13.6-ish. 13.6 down here. Sorry it got so small. But that's your answer. On average, that many pairs of people in a group of 100 share a birthday. A little over 13 pairs of people. And the linearity of expectations made it super simple to find that, because we just considered each pair separately. And like the 0 was nice, everything went to 0 most of the time, and like the one shined through. See that? And so we just add them all up. And so on average, that's how many people, how many pairs of people we can expect to share a birthday in a group of 100. So that's pretty cool. Very powerful result, very similar to the birthday paradox, but a little bit different, right? So I think the last major thing I want to tell you for these slides is called the binomial distributions. The last kind of major thing I want to talk about. It was invented by a man, I think his first name was Jacob or something that starts with J-A-C. His last name was Bernoulli. He's very famous. And so it has to do kind of with his name a little bit. So in the binomial distribution, we have things called Bernoulli trials. And those are where you have an experiment, and that experiment has two possible outcomes, either something that you determine to be success and something that you determine to be failure. So you have two options only. So you can consider coin flipping to be a Bernoulli trial, because you have two options, and you can be like, I really like heads, so I'll say that if the coin lands on heads, that's success, and if the coin lands on tails, that'll be failure. So for example, coin flipping. And the distribution over this random variable that you talk about in terms of these successes, the distribution over a random variable that you can make defined by the number of successes in a bunch of independent Bernoulli trials, those words are important, that's called the binomial distribution. And then I'll use the rest of the slide to try and unravel what that means. Okay, so like you are running a bunch of these Bernoulli trials, like you're flipping a bunch of coins, for example, and they're all independent of each other. Flipping the last coin does not influence the next coin flip. That never happens, right? So that's definitely going to lead to a binomial distribution, okay? And we care about the number of successes, counting that as a random variable. That's the binomial distribution, okay? So the probability then, this is how we unfold the binomial distribution and use it to solve problems. The probability that you have exactly k successes in a sequence of n total independent Bernoulli trials, so like the probability that you have k heads when you're flipping n coins total, all right, where you have a probability of success p and a probability of failure, because it's the only other option, right? It better be 1 minus p, we'll call that q. It's equal to this, all right? It's equal to n choose k times probability of success to the power of how many successes, right? Exactly k, times the probability of failure to the rest, right? N minus k, because it's got to add up to n trials total. And the choosing bit, the combinations here, is the order in which the successes happened depends, right? It could be like you have a bunch of successes at the front, or you have a bunch of successes at the end, or they're like interspersed. You can have a bunch of different ways to get successes, and so like we're trying to pick out what are all the different ways to get that many exactly k successes. So for a concrete example, let's show the binomial distribution at play. Let's try to calculate the probability of flipping exactly 2 heads when you toss 4 coins, all right? And we're going to notice where this n choose k comes into play. So just to use the formula, for example, here's how you do it. It's like I want the probability of flipping exactly 2 heads if I flip 4 coins total. Well, that means that n is equal to 4, right? N is equal to 4, and then k is equal to 2. We'll consider heads to be success. So that's going to be 4 choose 2 times the probability of success. Well, probability of heads, right? If that's our success, that's 0.5, of course, with a fair coin at least. And then we flipped 2 of them, right? 2 heads. And then times the probability of failure, which is 1 minus p, so 0.5 again for the probability of getting tails. You got tails also twice, right? Because they got to add up to 4. And like this is the order in which you got the heads. So the 4 choose 2, what's that? That's 4 times 3 over 2 factorial, so over 2 times 0.5 to the 4th, and that is going to be equal to let's see, that's 2 times 3, so 6. That's 6 times 0.5 to the 4th power, and that's 0.375. That's your probability, about 37.5% chance that that's going to happen, okay? And the reason this works out, the reason you have 4 choose 2 is because your heads might appear anywhere. Like you may, if you get really lucky in your first 2 coin flips, like those are where your 2 heads were. It could go heads, heads, tails, tails. But like there are 6 options here. And let me show you like where the heads go. You could have had tails, then 2 heads, then. You could have had the heads go together again and be at the end of your coin flips. Or they could be interspersed. You'd be like, it could be head, tail, tail, head. Right? That's another ordering in which you got 2 heads still, 2 successes. You could have done head, tail, head, tail. That could have been your order of your coin flips. Or finally, it could have been tail, heads, tail, heads. And if you think about it, these are the only 6 options for getting 2 heads when you're flipping coins, right? So that's where the 4 choose 2 comes from. And then the rest makes sense, right? This is the probability of getting those 2 heads, and then this is the probability of getting 2 tails as well. And they all multiply together. So that's how you use the binomial distribution to solve some interesting problems. And so that's going to tell you the expected number of successes in n trials, for example, if you start using expected value. So this was just probability, right? That was a probability thing. Now let's talk about expected value of how many successes I expect to see, all right? So the way you do that is you make a random variable. Let's say the expected number of successes for each trial. Make a random variable for each trial. And like make it be 1 if it was success and 0 if it was failure. So that's really easy. Like the expected value of this random variable that's 1 when it was successful and 0 when it was failure. It's, well, the 1 times the probability of success. So that's p plus the probability of failure times the 0, right? Because you'll just make the random variable be 0 when it's a failure. And the 0 part cancels and the answer is just p. So when you have n trials total, like you're flipping a coin n times, the expected number of successes, oh gosh, I can't even pronounce the word. The expected number of successes is n times p, which kind of makes sense. So, like, let's say we're flipping coins, right? What's the expected value that a coin flip, or coin flip CI, is heads? What's the expected number of successes? Well, it's just going to be the probability that you get heads, so that's 0.5. And this is kind of intuitive, right? Because that means if you flip 3 coins, thanks to the linearity of expectations, it's going to be like, well, 3 times 0.5. You expect to see 1.5 heads when you flip 3 coins. Does that make sense? That's pretty intuitive in my mind, at least, and that follows from the linearity of expectations. It's like, all right, the expected value of some constant, like 3 times our variable, that's equal to just bring the constant out and multiply that by the expected value of your random variable, which is equal to c times that probability p, because this is a random variable that's talking about the successes in a Bernoulli trial, okay? So that's pretty nice, because that all goes to 0. And so yeah, you flip 3 coins, you can expect to see 1.5 of them be heads. You flip 4 coins, you can expect to see 2 of them be heads, on average, across a lot of coin flips. Okay, that's kind of what it's doing. It's doing a weighted average, and that is the binomial distribution. So here's a fun example for you to try. Let's pretend that you're best friends with like a gambler somehow, and the gambler has a coin. They have a coin that's either fair, like that means it's equal probability if it lands, you flip it, it lands on heads or tails with both 0.5 probability, or it was their secret fake coin that is that helps them cheat. It's biased with a probability of heads equal to only 0.3. That means tails would be 0.7. Okay, and so either they're like flipping their fair coin right now, and like the probability of heads is 0.5. This is their fair coin. Probability of heads 0.5, or they're flipping their biased coin right now. You're just watching them flip some coin, and the probability of heads there is only 0.3. Without knowing which coin the gambler is using, you ask him to flip that coin 10 times, all right? And you say that, all right, I'll believe that it was the fair coin if I see at least 4 heads, okay? But if I see less than 4 heads, I'm gonna be convinced pretty much that your coin was the biased one. You took out the fake one, okay? So here are my questions for you. You're going to use the binomial distribution and these ideas that we've been talking about to calculate what's the probability that you're wrong and the coin really was fair, but you saw less than four heads. So you'll have to, my hint to you is to calculate the probability of seeing 0 heads, 1 head, 2 heads, 3 heads. Do them all separately and add them up. And then also, likewise, with a similar kind of style, what's the probability that you're wrong and the coin was biased? So you saw at least 4 heads. You saw 4 or more heads, and you said, oh yeah, that's the fair coin, but it really was the biased one. What's the probability you were wrong in that case as well? Okay? So think about both of those and use these equations here. It's going to be this one. It's going to be this one that you'll use. And you'll add them up and see how likely it was that you were fooled. All right. For the A case, the probability you reached an incorrect conclusion and the coin was really fair, that means you thought it was biased because you saw less than 4 heads. So that means you saw less than or equal to 3 heads. All right. And for B, we thought it was the biased coin incorrectly. We thought it was the fair coin, but the coin was really biased. What does that mean? We thought it was fair because we saw at least 4 heads. So that means we saw greater than or equal to 4 heads in that case. Okay? And so we thought it was fair, but it was really the fake one. All right? So that's what we're going to kind of calculate here. So the probability that we reach an incorrect conclusion, the coin is fair, is the probability that the biased coin really gave you that many heads. All right? Less than 3 heads. Less than or equal to 3 heads. So like that's the probability that the fair coin, right, was giving you this many heads. 0 heads, or it was giving you 1 head, or 2 heads, or 3 heads. You see how if you add these up, this is the probability in total that this happened. That the fair coin gave you one of those amounts of heads. So, doing our formula here, trying to calculate stuff using the binomial distribution, we're going to do n choose k, pk, q, n minus k. So we are flipping 10 coins, right? We're flipping that coin 10 times. So it's 10 choose. Well, I'm getting 0 successes for this one. 10 choose 0, right? Times, and then it's times the probability of success to the power of how many successes. So that's 0.5. It's really to the 0th power, right? Because I saw 0 heads. And then 0.5 probability of tails for the fair coin, that is. I saw 10 tails exactly. So that's how you do it. So 10 choose 0, 0.5 to the 0 times 0.5 to the 10. And we do that for all these. And this is 10 choose 1, right? I see 1 head from the fair coin. So that's 0.5 times 1 for that many heads. And so I must have seen the 9 tails, right? And if you add all these up, all the way up to 3, the answer is about 0.172. All right, so that's about a little over 17% chance you were fooled by the fair coin. It really did give you, it was fair, but it really did give you less than 3 heads, less than or equal to 3 heads. And that is possible. It's just unlikely. Okay, so that's where you're going when that's happening. And then for the flip side, let's say that you thought it was fair, like you saw at least 4 heads or more, but the coin really was biased. So what's the probability that you saw greater than or equal to 4 heads with the biased coin? So that's the probability that you saw 4 heads with the biased coin, or that you saw a probability of 5 heads with the biased coin, all the way to if you saw at most, right, the maximum 10 heads with the biased coin. It's very unlikely, but it's possible. All right, and so you're going to add all those up. That's going to be equal to what? This is now 10 choose 4 times the probability of the biased coin giving you a success, or heads, right? That's 0.3. 0.3 to the 4, because you're seeing 4 heads there, times 0.7. That's how many tails you got, and that adds up to 10, so to the 6th power. So if you do all those, that gives you 0.35. So that is a 35% chance that you were fooled by the biased coin, which is interesting. So like, even if you see a lot of heads, you conclude that it was fair, but it might have been the biased one. You got a lot of trials. They add up. So that's it's still better than 50 chance your 50-50 chance your strategy, at least, though. you're going to win in the long run if you bet against the gambler, maybe. But sometimes you will be wrong, and these are your percentages that you'll be wrong. And so that's a fun little idea, and I hope that makes a little bit of sense. And so for my last example today, let's bring it all back to computer science. So let's talk about hashing, right? Because that's something we care a whole lot about. We want to make sure that our hash tables are like wide enough so that we don't collide too often, because that's what the goal of hashing is, right? We want to make each bin, each bucket, whatever you want to call it, equally likely for every value that you could possibly put in your hash table, okay? And so what I want to ask, like the things that we can ask knowing what we know now, is like, what's the probability that there's a collision in our hash table when we have n buckets or n slots and we're trying to insert m keys into the hash table, all right? And again, the easy way to solve for this is to think of the complement and just subtract it from 1, right? So that the answer for this probability, it's 1 minus the probability that there were no collisions at all, all right? We're trying to find out the probability that there was at least one collision. So it's 1 minus the probability that there were no collisions at all. And we can simplify that into, all right, 1 minus the probability that the first key had no collisions times the probability that the second key had no collisions times the third key had no collisions, all the way to the probability that the nth key had no collisions. And so in the best case, and like every key was equally likely to pick a slot, that means it would be this probability that there were no collisions, right? Well, there's a 100% probability that there's no collisions the first time, but then you've used a slot, and so now there's n minus 1 left, all right? So this is the probability that the second one, right? The second thing that you insert is not going to collide. This is the probability the third thing is not going to collide because you used another index. You have n minus 2 to choose from now, all the way to n minus m plus 1 over m for the last mth key that you insert. And this formula leads to a very interesting realization. So even if you have a lot of room in your hash table, you have 2 to the 32 buckets to choose from. So that's like 4 billion-ish, right? And you only insert like less than 100,000 things. So that's barely any of the hash table like you're putting entries in. Even so, like that's how many entries you have, 32 bits worth of them. And then you insert that many values, you still end up colliding about 50-50 chance that you've collided by then, inserting less than 100,000 things in a hash table with 4 billion entries of room. So that's crazy. That's unintuitive. It's like somehow, like you have all this room, you're still going to be like ganging up on one of these indices somehow. You're going to have to like extend it and do your normal collision stuff. So that's crazy. This is actually the birthday paradox coming again to bite us. Like you have just not a lot of entries in your hash table, but you have all this room to place things. They're still going to collide, unfortunately. And so maybe like you use 64-bit numbers to represent you have entries that take up 64-bit numbers, so like 32 to the 32. That's how many indices you had with 32 bits. If you have a 2 to the 64 number of entries hash table, you have this many entries, and so that's quite a lot more. It's like you doubled it 32 more times. Then you have a little bit more leeway, but that's a lot of memory you're giving up at that point. So if you had this many slots, 2 to the 64 slots, then you're allowed to like insert a few million before the odds of you getting a collision after that many inserts becomes more than you being struck by lightning. So that's a very interesting graph that it's showing here that I stole from the internet. So that's pretty cool. But yeah, that just goes to show the power of the birthday paradox, right? You have all this room, and you insert just relatively few things, you're going to collide. And we know how to solve for that now, thanks to our newfound knowledge of probability. So yeah, I think that's where I wanted to stop for the lecture. That's all the pieces of information that I can give to you. You're now experts in probability. And yeah, I will see you next time.